Let's first consider this integrator circuit, which contains an opamp, a resistor, and a capacitor. We can solve this circuit in the time domain using the characteristic capacitor equation and in the phasor domain using complex impedances. Let's start with the time domain. First, we'll apply Kirchhoff's current law to this node here. This gives us that IR equals IC. Since both currents are the same, we can call them simply I. Next, denote the voltage across a resistor as VR and apply Kirchhoff's voltage law around this loop. This gives us minus Vin plus VR is equal to 0. Hence, Vin has to be equal to VR, which by Ohm's law is equal to I times R. This yields the expression for the current I is equal to Vin divided by R. Next, we'll denote the voltage across a capacitor as Vc and apply Kirchhoff's voltage law around the slightly bigger loop here. This gives us Vc plus Vout is equal to 0, and hence Vc is equal to minus Vout. The characteristic capacitor equation for C will give us an equation for I, namely I is equal to C times the first derivative of Vc, which must be equal to minus C times the first derivative of Vout. Substituting I in this equation yields Vin divided by R is equal to minus C times the first derivative of Vout. Hence, the first derivative of Vout is equal to minus 1 divided by Rc times Vin. Integrating both sides of the equation yields the final expression for Vout. Vout is equal to minus 1 over Rc times the integral of Vin between 0 and t. After solving the circuit in the time domain, we will now solve the circuit in the phasor domain. First, we'll replace the resistance R by its complex impedance ZR equal to R. We substitute the capacitance C by the complex impedance ZC, which is equal to 1 divided by J omega C. So here we can use the formula for the generalized inverting amplifier, which instead of the resistances Ri and Rf now contains the impedances Zr and Zc. Hence, Vout is equal to minus Zc divided by Zr times Vin. Substituting Zc and Zr yields minus 1 divided by J omega C over R times Vin, which gives the final expression for Vout in the phasor domain, namely Vout equal to minus 1 over J omega Rc times Vin. As you can see, it is possible to solve the circuit in the time domain, but also in the phasor domain. Solving the circuit in the phasor domain is often quicker and easier. Let's now consider this circuit containing an opamp, a resistor Ri, a second resistor Rf, and a capacitor. We will show that this circuit realizes a low-pass filter. Since the circuit contains a capacitor, it can again be solved in the time domain using the characteristic capacitor equation and in the phasor domain. We'll start again with the time domain. For this, let's start by denoting the currents. The current through resistor Ri will denote as II, the current through Rf will denote as If, and the current through the capacitor will denote as IC. Applying Kirchhoff's current law to this node here yields that II is equal to If plus Ic. Further, we'll denote the voltage across resistor Ri as Vi and apply Kirchhoff's voltage law around the small loop here. This gives that minus Vn plus Vi is equal to 0. Hence, Vin is equal to Vi, which by Ohm's law is equal to II Ri, so that we get an expression for II. II is equal to Vin divided by Ri. We'll denote the voltage across resistor Rf as Vf and the voltage across the capacitor as Vc. Applying Kirchhoff's voltage law to the small loop up here reveals that Vf minus Vc is equal to 0, so that Vf is equal to Vc. Let's denote Kirchhoff's voltage law again, this time going around the bigger loop here. This gives Vc plus Vout is equal to 0, which gives that Vout is equal to minus Vc, which must be equal to minus Vf, which by Ohm's law is equal to minus If Rf. This way we get an expression for If. It's equal to minus Vout divided by Rf. To get an expression for IC, we'll apply the characteristic capacitor equation to the capacitor. It gives us that IC is equal to C times the first derivative of Vc, which is equal to minus C times the first derivative of Vout. Now we have found expressions for all currents in the circuit, II, IF, and IC, which we can substitute into our KCL expression obtained at the beginning. This gives us that Vin divided by R is equal to minus Vout over Rf minus C times the first derivative of Vout. Multiplying both sides with minus Rf yields Vout plus Rfc times the first derivative of Vout is equal to minus Rf divided by Ri times Vin. This is an ordinary first-order differential equation for which we know the solution. Vout is equal to minus Rf divided by Ri times Vin times 1 minus e to the power of minus t over Rfc. After solving the circuit in the time domain, we will now solve it in the phasor domain. First, let's replace the resistance Ri with the complex impedance Zi, which is equal to Ri. Next, we'll combine the capacitor C with the resistance Rf to the complex impedance Zf. Since Zf is a parallel connection of Rf and C, its formula is given by Zf equal to 1 over Rf plus 1 divided by the complex impedance of the capacitor C, which is 1 over j omega C. So that Zf is equal to 1 over Rf plus j omega C, which can be simplified further to Rf over 1 plus j omega Rfc. Now we can again use the formula for the generalized inverting amplifier. It gives that Vout is equal to minus Zf over Zi times Vin. Substituting Zf and Zi gives minus Rf over 1 plus j omega C Rf divided by Ri times Vin. So this gives us already the final expression for Vout. It's equal to minus Rf over Ri times 1 over 1 plus j omega Rfc times Vn. Again, we have seen that this circuit can be solved in the time domain and in the phasor domain. To better understand the input-output relationship of this circuit, we will now draw the magnitude of Vout over Vin as a function of the frequency omega. For omega equals 0, the magnitude of Vout over Vin is simply Rf over Ri. As omega increases, the magnitude of Vout over Vi decreases and slowly approaches 0. Of special interest to us is the frequency for which the magnitude has dropped to 1 over the square root of 2 of its original value, hence to Rf over Ri times 1 over the square root of 2. This frequency is called the cutoff frequency omega c, and here it is equal to 1 over Rf times c. For frequencies below the cutoff frequency omega c, the magnitude of Vout over Vin only drops to about 70% of its original value. Hence we say that those frequencies pass the filter, and we call this band of frequencies the pass band. For frequencies above the cutoff frequency, Vout gets attenuated. Hence we say that those frequency components are filtered out or stopped, and we call this frequency band the stop band. Since in this filter only low frequency components are passed, this is called a low-pass filter.